Green. I'm the Executive Vice President at Wake Tech, and on behalf of our President, Dr. Stephen Scott, I'm very pleased to welcome you here this afternoon. It's exciting to see such a great crowd who's interested in science. And now it's my pleasure to introduce Adrienne Lineback. She is an Associate Professor of Geology at Wake Tech with MS and BS degrees in geology from East Carolina University. Through a grant funded by the National Science Foundation, she and Gretchen Miller have guided the overall administration of the project, which has involved a collaboration between Wake Tech and NC State geology faculty to provide research opportunities to students who are interested in geosciences careers and want to transfer to NCSU and other four-year colleges. Adrienne and Gretchen have done a ton of work, so let's give them a big round of applause.
Hi, everyone, and welcome. We're glad to see you here. A few housekeeping things to make note of first is please make sure your cell phones are off, and no pictures or videos during Dr. Schmitt's talk, please. If you need to use the restroom, if you go out the back door, it's just across the hall. If you go out this way, it's left and left again. Dr. Schmitt does not sign autographs, but he will sign copies of his book, which are available for purchase just outside, and he will be out there after the talk signing those books. Finally, Gretchen Miller and I would like to thank all of the people who made this event possible. And I can't take time to read them all because it's a pretty long list, but on the back of the programs that you have there, please take a look at all the people that helped to contribute and make this happen. Senator Harrison Hagen Schmitt was born in Santa Rita, New Mexico, grew up in Silver City, and received a BS from Caltech and a Harvard PhD in geology. He earned his jet pilot wings in 1965 and helicopter wings in 1967. Selected by NASA as a scientist astronaut in 1965, Schmitt flew in space as a lunar module pilot for Apollo 17. He landed in the valley of Taurus Littrow, December 11, 1972, as the only scientist and last of the 12 men to step on the moon. He was elected to the U.S. Senate in 1976, and Schmitt more recently chaired the NASA Advisory Council from 2005 to 2008. He served as lead director for Orbital Sciences Corporation prior to this year's merger of that company with the aerospace and defense company, ATK. Schmitt now chairs the governance board as a member of the Orbital ATK Board of Directors, and please help me in welcoming Dr. Harrison Schmitt.
Thank you. John, Nicole, where are you? There you are. Cousins. They stole my middle name. How many would like to go to the moon someday? Oh, that first question didn't get very many hands this morning. This morning I asked how many in the audience were planetary or lunar geologists. I was the only one that raised their hand. What we're going to do this afternoon is not require a PhD in geology or anything even equivalent to that, but to take a trip to the moon as fast as we can in the time available. This whole period of Apollo was a unique period, obviously, in the history of the United States and indeed in the world. And I think it's important to start off on a serious note. I presume there's some computer clever people in the audience. But I think it's important, particularly for younger people, to know a little bit about the history of Apollo, and we'll go through that very, very quickly. This was an idea that had been around for some time. NASA had been working on it. through a group called the Space Task Group, led by Bob Gilruth, who later became the director of the Johnson Space Center, then the Manned Spacecraft Center. And NASA was at the time quite confident that this mission to the moon was possible. They didn't know exactly how they were going to do it, but they were able to persuade and convince Vice President Johnson and President Kennedy that this would be a way to score some very, very important geopolitical achievements within the context of the Cold War. And that's what I think we all have to remember, is that this was a Cold War program, that science was not a major issue. It was discussed. There was a science directorate at NASA at the time. But nevertheless, it was something that was felt necessary from a psychological and philosophical point of view for the United States to do in the context of the Cold War. Neil Armstrong, of course, successfully landed on the moon on 20th of July, 1969. That effectively ended the moon race, although certain aspects of the moon race had gone in favor of the United States for some time. And as Russian emigres have told me back a long time ago, the successful launch of a Saturn V, which you see in the background of this picture, on a test flight, pretty well convinced the Russian leadership that they were not going to be able to beat the United States to the moon. There were 5 additional Apollo missions that landed on the moon between November 1969 and December of 1972, and I think it's wise to remember that all of this was done by young people. The average age at the time of the Apollo 13 mission, the mission that had the explosion and was rescued and brought back to Earth successfully, the average age of engineers in Mission Control Center and really throughout the agency and the contractor force was about 26 years old. And they had already been at work for a long time, several years, because of the earlier missions. They were managed by people in their 30s and maybe early 40s, but it's important to realize when you take on these kinds of complex national and engineering efforts, it takes young people to make it happen. And people who can have the stamina and the courage, the motivation to see it to a conclusion. In terms of stamina, we all felt that we could work 16-hour days and 8-day weeks, and indeed we did. It pretty much seemed to be the way it was going. But always keep that in mind, that young people are the critical ingredient here. The last 3 Apollo missions each explored different areas of the moon, as did the first 3. But in the case of those last 3, including Apollo 17, that we were on the moon for 3 days. We had upgraded spacesuits and a modified sort of a Block 2 lunar module that could land more payload. All of this made for some great exploration efforts. 850 pounds of lunar samples were brought back to Earth. Those samples really are the gift that keeps on giving. There's the research that has taken place over 45 years or more on these samples is just remarkable, and it keeps getting better. Primarily because of the continued interest of young people in lunar science, but also because technology keeps moving. Engineers keep driving the sensitivity of instruments and down to where now we're using lasers to date, to get age dates, isotopic age dates on extraordinarily small pieces of these rocks, which is changing our perspective on how these rocks formed and when they formed. And of course, all of this, in one way or another, directly or indirectly, relates back to the new understanding we now have of the Earth's early history because of our understanding of the history of the moon. The moon's activity ceased, major activity ceased about 3 billion years ago with the last of the major eruptions of basaltic lava. But really the major features of the moon were formed before 3.7 billion years ago, and the big craters and the like. And that was a time, about the time when replicating life began to appear on this Earth. So it's important now to integrate that understanding of the moon into our speculations about the origin of complex molecules on Earth and the kind of violent environment in which they were exposed. We talked more detail about that this morning. Well, you may be familiar with this picture since we're in North Carolina, but it is, nevertheless, it is remarkable that from 1903, in a very short amount of time, John Glenn and Al Shepard and others were in space. It's quite a history and quite a legacy for the state. This, of course, is John trying to explain something to the president about the inside of his spacecraft. John never could explain it to me either. This happens to be the crew of Apollo 11, but in this case, they are awaiting, as I recall, the reappearance of the Apollo 8 spacecraft from behind the moon. You remember that you go into radio silence when you go behind the moon, and one clue on how successful your burn out of lunar orbit has been, the rocket pulse out of lunar orbit has been, is whether that communication comes in exactly at the right time. And that's what I think we were waiting for here was things. And there's Mike Collins, Neil Armstrong and Buzz Aldrin standing, yours truly, and Ken Mattingly, who flew on Apollo 16, is also in that picture. That's mission control, by the way. And this picture, I think, is the only picture that Buzz Aldrin took of Neil Armstrong on the moon. We won't go into why that might be the case. But it is a very important picture historically as well as scientifically, because Neil is in the process, as he told me, of filling up what we call the lunar rock box with soil. He had collected a magnificent suite of samples from the area around the lunar module Eagle. But when he put them all in the box still looked empty, more or less, to him. And so he filled it up with soil. And that soil has become one of the most important soil samples, probably the most important soil sample that we ever got from the moon. It has told us a great deal about the resource base that we have on the moon for both settlement and for potential energy use here on Earth. We had all sorts of training, most of it in computers, but it was decided that we needed to know how to survive in jungles. And of course, that related to coming back to Earth, not going to the moon. And so we all spent several days down in the Air Force training facility in Panama. And here you see a bunch of astronauts trying to figure out how in the world do you use the palm tree for shelter. And it rained all the time, and we never figured it out. I did figure out how to make an excellent heart of palm fish soup, though. Anybody wants a recipe, just let me know. And I also got a second career as a bandit, apparently. Okay, the Apollo 17 mission is landed approximately where you see here, or in the rim of a crater called Serenitatis, a basin, 740 kilometers in diameter, so I guess we'll call it a basin. Neil landed at the Apollo 11 site, as indicated here. They're about 600 kilometers apart. Ended up providing very, very different information about the history of the moon. All right, now this picture gives you, I think, some perspective about the Saturn V rocket. The Saturn V is the largest rocket yet used to put human beings in space. It weighed, fully fueled, 6.8 million pounds. The thrust of the 5 F1 engines in the first stage reached, at liftoff, reached 7.5 million pounds. Enough, of course, to get us started. Took about 10 minutes to get into orbit. The first stage was extremely rough. Heavy vibration, low frequency. I don't know whether any of you have ever driven your pickup truck down the ties on a railroad track at about 30 miles an hour. That might give you an idea of what we were experiencing. I don't know what pickup truck I would recommend doing that in, but the second stage, though, had 5 engines, but they were hydrogen-oxygen engines rather than kerosene-oxygen engines, and they were very, very smooth, as was the third stage, the Saturn 4B, that eventually accelerated us to the moon. But the change from first to second stage was a change from a 4.5 gravity acceleration, 4.g acceleration, to a minus 1.5 when those engines shut off, the whole stack sort of unloaded and decelerated a little bit, and then back to a plus 1.5 on that second stage. That all took place in about a second, slightly more. So that gets your attention. You know why you're wearing seat belts and shoulder harnesses and things like that. And don't have anything loose in the cabin, believe me, it goes all over the place. I wanted to, again, give you some perspective on the size. This is a very large fire truck parked outside the vehicle assembly building. That building was the largest enclosed space in the world at the time. That was first exceeded by the Mall of America in Minneapolis. And now I think it's exceeded by the new 787 plant in your neighboring state to the south. I believe that is the largest enclosed space in the world right now. Not sure, but it's big. But anyway, this was big at the time, and it was built to handle the assembly of 4 of these rockets simultaneously. They would not be launched simultaneously, but they would be in various stages of assembly. The space shuttle was assembled in this building as well, and now I think NASA's trying to find contractors that want to use it. Our spacecraft were positioned as you see here. Lunar module all folded up in the just below the command and service module. And also in this picture, if you look carefully, you may see right there what are indeed large chunks of something coming off the spacecraft. Well, that's frost, ice. We were 22 hours and 40 minutes delayed on the launch pad due to our launch computer misunderstanding the status of the launch vehicle. And it didn't take very long to figure out what the problem was. It took most of that 2 hours to convince management that they understood what the problem was. Nobody's ever had that problem. But the ice, that heavy vibration broke almost all of that ice off the rocket, so we didn't carry it very far. It would have been a serious reduction in our payload had we been carrying it. Now, this is a picture not to show you how much things have changed from my physical perspective, but I want to illustrate the suit to you that we wore on the moon. Anything in blue is an input to the suit. Anything in red is an output. We had oxygen and communications, and this is a water port that I know all of you wonder, how did you stay cool on the moon? Well, we had the personality to stay cool. But also we had water-cooled underwear. Long-handled underwear. You don't use that in North Carolina, do you? Yeah. Anyway, long-handled underwear, I'm sure you've heard of it, with little interconnected tubes sewn into it through which cold water was circulated. And we produced that cold water in our backpack by sublimating ice out of a port in the back of the backpack. That has confused some geochemists who measured water on the moon, and they suddenly realized that it was the sublimation of ice that we had on our backpack. Since we found water on the moon, so that's all gone away. The exit ports, of course, are the exhaust. Now, what happened? What we did was the suit circulated the used air through lithium hydroxide canister. You don't have to remember that. There won't be an exam. But that removed the carbon dioxide, and then it was recirculated back in the suit. But we also had an emergency backpack. We had a backpack on top, you'll see it here in a few minutes, that contained a high-pressure bottle of oxygen. And it was sufficient that if we opened this port to the vacuum, that we would still have about 30 minutes of oxygen through that port. Or if the suit became torn or something like that, we would have quite a bit. It was just an emergency oxygen bottle. You've seen that, and we've talked about the ice coming off. Now, this is we spent 2 orbits of the Earth, 90 minutes each, letting the ground look at all of the telemetry systems that we had on the third stage rocket that we were going to use to go to the moon, and the spacecraft and other things, and make sure that everything was ready for us to depart. But I also want you to just remember this little band of blue here above the clouds over the North Atlantic. That, of course, is our atmosphere, and I'll call your attention to that in a few moments. This picture of a nearly full Earth is one that I took from about 34,000 miles above the Earth, showing, of course, essentially all of Africa and most of Antarctica, as a matter of fact. And if you look at some of the weather patterns, I took this picture to begin the documentation of 3 days of weather observation and forecasting that I did on the way to the moon when things were not, other things were not happening. And this, for one thing, you can see here is a hurricane or cyclone going ashore on India, the subcontinent of India. Also see these weather patterns around Antarctica, much more symmetrical than what we see in the northern hemisphere, because there are fewer land masses to interfere with their progress. And then down here, the South Pole and the Southern Ocean. By the way, the ice cover in this part of the world is extended way out here now. It's getting back to Shackleton times, as we talked about at lunch. Really quite remarkable cooling of the ocean down there. Now, remember that band of blue around the Earth? Well, you don't see it around the moon. Essentially, it's hard vacuum. It's a space vacuum, 10 to the minus 12 torr for people who like numbers. And there's a transient atmosphere. There are some light volatiles, hydrogen, helium, coming off the moon, being released by small impacts. Then the moon just does not have the gravitational field to hold any kind of gas to it. This is a picture of the far side of the moon, of what we call the lunar terminator. On the far side of the moon, it's actually a lunar sunset terminator, whereas it was our sunrise. We were in what, astronomers like to call a retrograde orbit, and I'll let your kids explain that to you. It means we were going around the moon opposite to its very slow rotation. Now, the Valley of Taurus Littoral. This is where we were headed. It's a deep mountain valley on the moon. It doesn't look particularly deep because the mountains have all been worn smooth. They were formed about 3.2 billion years ago. If you look carefully, In the center of that picture is the spacecraft America, right there. That is the command and service module. Ron Evans is all alone in that spacecraft now. Gene Cernan and I have been in the lunar module now for some time. This picture was taken from the lunar module on the last orbit before we ignited the descent engine in the Challenger and descended down into the valley. Ron is in the process of taking navigation sightings on some small craters here in the valley, and our landing point, by the way, was going to be right there, right between those two craters. That was sightings he was making of craters whose position had been determined using what's called photogrammetry on some pre-mission photography relative to the center of mass of the moon. And it's very important. You navigate relative to the center of mass of the moon, not to the nature of the features on the surface. And that information was then processed back on Earth and then transmitted up to the lunar module, Challenger, so that we had a better understanding, as good as understanding as he did, of the nature of the position of his orbit relative to the moon and the center of mass. So very important for being able to have a precise landing in this mountain valley. The valley dimensions, this mountain is 2,100 meters high, or over 7,000, or about 7,000 feet. This one not quite that high, so it was much like deeper than the Grand Canyon. This dimension right here was about 7 kilometers. I have to translate to miles. I'll let you do that. But interesting enough, we built these rockets. The engineers built these rockets using the English system of measure. We flew them using a nautical system of measure. We always talk nautical miles. And we've worked on the moon using the metric system. And at least we were able to keep that straight somehow. That didn't happen with one Mars mission, as some of you may recall. But it worked out very well for us. But now when I talk about it, I have to do all sorts of translation, and I don't always get that right. One of the features that we talked about this morning, just this plume-like deposit here, is actually the remains of an avalanche that came off the side of the South Massif here. Probably triggered by a fault, a major moonquake along this line right there. You may see that again in a little while. This is the camp that we established on the moon, the Challenger, an excellent camp. Actually had the capability to stay for at least 4 days, but we compromised with other scientists, let them put some payload on, and took that stay time down to 3 days, which was a great 3 days, but it always would have been nice to spend more time. One of the things that happens when you land on the moon is that the effluents from the descent engine, gases from the descent engine, winnow away fine particles from the surface and cause it to get a little bit lighter, because those fine particles are dark. They have in them some very fine particles of iron, which makes them dark. But when you walk on it, you stir up the dark material again, and here you see my footprints out here that have stirred that up. And that means that anytime you fly around the moon, and some of you may do that, and you can look down at one of these landing sites, you'll see where the lunar module landed because of that light area in it. And I'll show you, you'll see some more of that here in a little while. Now, all the equipment and everything we needed to work on the moon is here, including an astronaut and another astronaut, Gene Cernan, reflected in my visor there, the lunar rover, the camp, and of course the tribute to the American taxpayer that paid for all this. One of the problems you have when you have commanders on these missions is that they tend to break fenders off the lunar rover. That happened on all 3 of the missions that had lunar rovers. The commanders broke the fenders. Well, lunar module pilots like myself find out what you're paid to do, and that is repair fenders, right? So I have become an honorary member of many automotive repair societies. But this worked out very well. Actually, we didn't do the work. The ground, all we did was implement what they said. We told the ground what had happened, of course, and they went to work that night to figure out what we had. They knew what we had in the cabin, and they came up with this fix, which are some unneeded photo maps, chronopaque photo maps, that taped together with gray duct tape, right? And clamped on the fender with some light clamps that we really didn't need in the lunar module. Why they were there, I'm not sure. They were there in case you ever had to work in the dark in orbit, but we certainly didn't need them on the surface of the moon. So those are the clamps right there, and this worked very well. And the reason it was important is that in 1/6 gravity, which is the gravity of the moon, 1/6 Earth gravity, as you drive, you're going to get particles moving up these cleats and actually gives you a forward rooster tail. And some of that comes down on you, on your suit, on the radiative surfaces that we had for cooling certain electronics, so forth. So it was important that we get a new fender put back on the rover. Now here's yours truly in the suit now on the moon, and I mentioned to you the emergency oxygen supply. That's right there, and these are and they're tubes coming from it down that are connecting to those ports that I mentioned earlier. This is the main backpack, the camera, the Hasselblad camera that we use. Really excellent. It was the first time Victor Hasselblad put a motor drive, a battery-powered motor drive on his camera. And he did that, quote unquote, all for free. But of course, Hasselblad benefited from being on the moon, believe me, a great deal. Now what I'm working with here is a sieve. We call it the rake, but really it was a sieve. It was to get a certain size, concentrate a certain size of fragment that the idea was that some of those fragments had come from long distances thrown into the valley from other parts of the moon. Working in this suit was really quite easy comparatively to what it might have been. I could run across the moon using a cross-country skiing technique quite efficiently. And that, I think, for those of you who go to the moon in the future, think about that. Learn how to cross-country ski, and you can move quite efficiently across the moon. Of course, that you don't glide on the surface, you glide above it. But in 1/6 gravity, that's the way to go. The weight of the suit is about 370 Earth pounds, but you get to divide by 6, and you know the weight. Mass doesn't change, as Charlie Duke found out when he tried to jump straight up and forgot that his center of gravity had been moved back a couple inches, and in the television picture, he just sort of rotates right out of the picture. We're never going to let him forget that. I'm not sure I would have remembered it either. But now, one of many objectives we had scientifically was to investigate this big boulder. It's one of the few big boulders we could see in the pre-mission photography at the resolution of that photography. This boulder had rolled down the side of the mountain, rolled about 1.5 kilometers from a source that we could spot because it had a boulder track behind it. The lunar module's out over there, and if you look carefully, you can see that light-colored area around where we landed right there. But anyway, this boulder track now, if you again look carefully, that's the near edge of the track. These are my footprints going down inside, out of sight, and then up the other side. That track formed about 16 million years ago. That's when that boulder rolled down. Things don't happen very fast on the moon. In fact, those tracks will stay there recognizable for at least 1 million years and maybe 2 million years. Better than Washington, folks. Better than Washington. Again, that's the South Massif out here in the distance. This slope, it may not look it, but this slope actually is about 20 degrees. It was a pretty steep slope, and working on it meant that you were always leaning into the slope, of course, a lot. Well, one of the big discoveries of our mission was this lunar volcanic ash, the so-called orange soil. We didn't know it was volcanic ash until it had been investigated in the back on Earth. It's made up of very tiny beads of orange glass. These beads are average about 40 microns in size, and they formed when you had eruptions of lava, liquid rock, on the lunar surface about 3.5 billion years ago. I use big numbers here. And as soon as that lava, driven by gases, hit the vacuum of space, it would break apart and form these very tiny small spheres. And that's what we found here with this orange glass. Interestingly enough, there was black glass, black soil, black ash underneath it. We put a core tube, about 70 centimeter core tube down about right here, down into that black. We didn't know the black was there until we pulled the core tube out. The bottom part of it was black. It's become a very important part of the debate on the origin of the moon because of the presence of high volatile concentrations in the ash. And indeed, about 3 or 4 years ago, a team at Brown University was able to look at the inside of some olivine crystals in this glass and found indigenous lunar water. So water was part of the process of driving these pyroclastic or these volcanic eruptions. Well, here I seem to be having a great time. This was probably between the first and second, or second and third EVA when this picture was taken. I apologize for being in my underwear and not in what we call our constant wear garment. It looked a little nicer, but that's all right. And one thing, though, to look at here is this descended vein in my forehead. One of the things that happens physiologically when you go into a reduced gravity is that fluid shifts to your upper body. Gravity's holding it in our legs here, and the fluid shifts, and you gradually eliminate that fluid over a few days. But apparently, at this point, there was still some of that distension of the vein and a little bit of edema in my face as a result of that lower gravity. This is a picture I took out of my window again that shows you a little bit about the nature of the lunar regolith, this debris layer that covers the moon. It starts to get stirred up. It has very high bearing strength initially. You can walk on it, don't sink in very far, but as you work, you're going to stir it up, and that bearing strength gradually disappears. It's in that regolith that we have our resources, though. This is what Neil Armstrong sampled, put in the box. And in analyzing that, we find that a great deal of, over time, a great deal of solar wind gas has accumulated in this debris, in this regolith. Most of it's hydrogen, a couple hundred parts per million hydrogen, a couple hundred parts per million carbon and nitrogen, and a significant amount of helium, all coming from the sun and being embedded in the soil. The helium also contains a light isotope of helium that is the subject of the book that I'll be signing. This helium-3, which is based on our work at Wisconsin, is a nearly ideal fuel for fusion power. And maybe someday we'll find a way to utilize this resource base on the moon for fusion power, which provides, and there's no radiation developed in the process. There's no residual radioactivity or anything like that. So it's a nearly ideal fuel for electrical power production. Well, we finally had to leave the moon. It was about 75 hours after we got there. Gene Cernan asked me to go get a really good picture of this liftoff. I declined, apparently already thinking about a political career of some kind. But we'll leave that to some of you in the audience who happen to go back to the moon and to stay long and wait for a liftoff that you can take a picture of. Now, once we, of course, went right up into orbit, but this picture taken by the current spacecraft around the moon, which is called the Lunar Reconnaissance Orbiter, very high resolution, and you can tell that because if you look carefully, you can not only see the trail, my footprints as I carried out the lunar science package out here, the experiment package, but you can see the rover tracks. And so the resolution here is on the order of 20, 30 centimeters, a linear resolution anyway. So it's a remarkable spacecraft, and it's really giving us a lot of new information about that I'm in the process now of integrating into the field geological story from the Apollo 17 mission. Let's see, I think, yeah. Now, the rover parked over here. The experiments were over here. There's the descent stage, our launching pad from the moon. And all of the missions show that the flag is still there. Its shadow is showing in all the mission photographs from the Lunar Reconnaissance Orbiter. And this has gotten DuPont very, very interested because it's a nylon flag, and one would not have expected the flag to survive the UV environment that is so intense on the moon. So my understanding is that the archives are being searched to try to find out what the formula of that particular nylon was, because we could certainly use it in New Mexico. Nylon doesn't last very long out there. Anyway, the ascent stage of the Challenger are now rendezvoused with Ron Evans and the America we spent a couple more days in lunar orbit. It gave me a chance to study some features from a distance that I had been looking at, and also gave us a chance to catch up with what Ron had been doing. And one of the things he had been doing is conducting an experiment. We always like to give the engineers a hard time, even though they made all of this possible. The way they had developed to power our spacecraft, of course, were fuel cells that combine hydrogen and oxygen to produce water and electricity. Well, the water we use for drinking and eating and reconstituting freeze-dried food and the like. But we all discovered that some hydrogen always got across the catalytic bed into the water. And here you see Ron has succeeded in getting that hydrogen into one big bubble in a particular packet of food. Now, the experimental food packet of choice was salmon salad. There was nothing wrong with it. It wasn't spoiled. Nothing. It just, fish does not travel well. And we never put it on our menu. Believe it or not, we were able to select our meals, and they were all tied together with fish line so that they came out in the order in which we had ordered them. But salmon salad always appeared. NASA was trying to get rid of it because it always came back. And anyway, when you go into a museum and they have a display of Apollo food packets, you may see some salmon salad. And just remember now that that's what we brought back, not what we used. And if there are any archaeologists in the room, you need to remember that when you look at middens around ancient dwellings, that may be what you're looking at is what they threw away, not what they were actually using. Well, we re-entered the atmosphere after 3 days coming back at about 25,000 miles an hour. At 10,000 feet, the main chutes deployed, and we drifted down towards a splashdown in the South Pacific, not too far from the island of Samoa. This, of course, was a splashdown of the last of the Apollo series of lunar missions. And we, again, were met by the carrier Ticonderoga. Any veterans of the Tyco in the crowd? Every once in a while you run into one. It was a very, very active carrier for a long time. In fact, Ron Evans flew two Vietnam missions, two Vietnam tours off the Tyco, so he was coming home. Now, I'm sure maybe some in the front can see this, but you wonder who these people are down here. Well, of course, they're the great Navy SEALs. They were actually called UDTs, Underwater Demolition Teams at the time. And they got everything squared away so we could get into this raft. And I think I can identify who's who. I think this is yours truly because I still had black hair at the time. This is Ron Evans because he was bald, and he was probably bald from birth. And Gene Cernan is in slightly gray, and now he's been totally gray for a long time. So I think that's who's sitting around down there waiting to get into the helicopter for the flight over to the carrier. Well, ladies and gentlemen, just to summarize a little bit, we had a wonderful period of time for the country, for science, for engineering, and of course for just having a new perspective, I think, about our Earth. And this picture just summarizes it. Again, if you look carefully, you can see that Gene Cernan is silhouetted as image there in my helmet. And for those of you who are interested in going to Mars, this might be the view that you have as you leave the moon on the way to Mars. Mars is a good moon is a good way station for resources, for learning, for training, and the like. And I suspect that when we finally get realistic about ultimately going to Mars, that the moon will play a major role in that process. So with that statement, it's probably wise that we take another walk on the moon. Thank you very much.